So, so these are the players. Okay, so these are the different industry players. IBM has its own environment for new experience or IBM 360. Then we have eBay, Leap or Ocean Index Software Framework, CAD's Forest, Google's Quantum Playground, TensorFlow Quantum, and Search. Then Microsoft LI3UIL, QSharp is their programming language for quantum computing. Similarly, Amazon Bracket is a complete new quantum computing as a service hosted on Amazon Cloud.
How many of them are open source and how many are paid?
IBM, you don't need to pay anything. Then Xanadu is open source. You don't need to pay for Xanadu Cloud as well. Microsoft, I think I have not used, but I think it is also open source. Amazon is paid. Amazon, you can't have, you can still have some basic initial couple of dollars, some $100 or so free credits and all. But beyond that, you have to pay. Similarly, Google is open source. For Google also, you don't need to pay. So, and then eBay, Rigetti, these things are proprietary. So, accordingly, you have to choose them wisely. Same with quantum. So now we have multiple different software vendors providing the quantum computing as a service on their respective clouds, or they are exposing their hardware. Either some of them also have a mechanism to physically actually deploy some systems. Some OEMs are like that as well, cryptographic applications, etc. For our FDP as well as most of the things we can do by sitting here, for those we will restrict ourselves to a couple of players like IBM, then Google and Xanadu. So apart from that, similar analogy goes with everyone else. Again, there are a couple of frameworks like Amazon Bracket can integrate with IBM QST. Similarly, Manycase is a generic software framework for quantum computing, which can accommodate and work with multiple different types of quantum computing services. Strawberry Fields of Xanadu is a specific software framework only for photonic quantum computers and associated algorithms, etc. So, we stopped here in our previous session, and this is a line which was quoted in one of the NASA talks in where several players in the Airbus, NASA participated in, say 2-3 years back. And this is what the NASA Quantum AI Lab director actually quoted in his talk. Like, best way to follow to know what is going on in quantum computing is basically to follow the research and not the press release, because mostly there will be hype in the press release or misinterpreted information. And if you really want to know where actually the progress is happening, both in hardware, software, any area, quantum algorithm, the research is the correct place to actually look at it. Again, research is not again easy. So, what we can check is there is a PPT from Microsoft several years back, 4 years back, and this is the best source. If you can even just search on Google quantum computing for computer scientists, there is a YouTube video with the same name, okay, from somebody from Microsoft. And this is the best place to understand the mathematics behind superconducting qubits related analogy. is the best place we should go for. And this is Microsoft PPT. So I have logged into IBM. You will have to generate an API token on your registered email ID in order to get them copy it here, that comes, and then once you get that token, I think you can run jobs and then use IBM database. You can have your dashboard, your compute resources, etc. IBM Quantum platform, and there is something called as IBM heuristic textbook also. So here you can sign in. So the same thing exists in other places. You can run this on IBM cloud. I'm just checking. So what I advise you to run our sample programs, you will need to log into IBM tools. So I think you should do that. These are runtime on IBM cloud. Yes, you will have to generate your IBM ID to your personal email ID. And then you will get all the resources. You have got the IBM basic documentation, tutorials, and you will open up IBM lab. Once you click on IBM Quantum Lab, cloud computing server will be allocated to you to this quantum cloud computing service. So now what I have done is I have logged into IBM heuristic. Okay, so get that API token on your registered mobile. Yes, you will have to create IBM ID. Your personal mobile and then you will get something like that, and then go to IBM Quantum, then within IBM Quantum you will get IBM Quantum Computing Lab here. So you can go here, you can sign in. I will walk you again. Type IBM go to IBM Quantum, go to heuristic. Here you will see the lab tab process. The moment you click the lab tab, it will land you here. Here. Still open up the net. Yeah, so what I said is that you go learning.quantum.ibm.com/catalog/courses. learning.quantum.ibm.com/catalog/courses. Once you have the login done, after that, once you go here, you can see this lab directly named to lab. You know the name. Once you go here to lab, you will end up opening up the lab notebook. here. Or you can go to IBM and then you can click the tutorials, and then obviously from tutorials you will land up here in lab. You can also click the documentation to understand multiple things related to setting USB, etc. In the way we have compiler, we have something called as a transpiler. So whatever you are writing, while writing a quantum computing program, there is a software at the back end which converts your code and I am not moving anywhere, so I am not starting. I have just opened in this lab notebook. So you have to go here. So first you do IBM QSP login. The moment you do IBM QSP, for example, you sign in here, you will go here. Okay. This is where you should come. If you click on sign in, you should get this window, IBM Quantum Platform, where you will have your own API token, etc. And from here also, IBM Quantum Lab, you can directly click here. Most probably it should land you to the Jupyter notebook. Yes, it will land up to a separate Jupyter notebook. So you can log in and then you can scroll down under the learning tab. You can click on IBM Quantum Lab. So first step is register on IBM QSP, create your login, get the API token, enter it here, edit from here and sign it. So it's Jupyter Lab notebook only, but at the back end, this is under IBM Quantum Learning. So you have IBM servers that are helping you to connect through their quantum computing cloud computing service, cloud service for quantum as a service. No, because it should support the IBM infrastructure at the back end. So it will run, but it will give error if it is not connected to an IBM cloud. So you will need the API token to log in, because see here if I go, if you are logged in, then there is no issue because you are connected to IBM cloud. So which means that you can use those libraries, you will not get a error message. Yes, correct. But Jupyter Lab notebook can be connected to any other infrastructure, right? So if you provide the right credentials to connect for different quantum hardware, you can do that. For example, using NLN, we can connect NLN to another hardware. So through NLN also we can connect to IBM cloud and through the software. Whatever we did here, using the mechanism provided by IBM for registering the credentials, API token and all, programmatically you can pass it on to Jupyter Lab for connecting some other quantum computing hardware. Any cloud services similar to that. It's a multi-factor authentication. No, credit card, I don't think credit card. IBM won't ask for credit card. Amazon asks. API token is only needed. I don't think credit card details are needed. No, credit card details are not needed. Just copy it. But you can make that.
I don't know from where what you click.
You must have got an email from the API. login. Google here also you can log in through your Google and maybe you might get some authentication. It takes some time to install. Some people are getting stuck where you are, but others are able to do it. I don't know. No, I need police security, not cloud login. I need police security. They need some multi-factor authentication, that is what they need. I guess if IBM ID is not working, you are logging up to Google credentials. Google also you can do it, no, it is not doing. So I think for some computers, I don't know why it is.
No, the computer is not there. It's on the Chrome.
It is on the
Firefox, it is on the Firefox, the same thing. But she is working on the laptop.
QScript login. You have to do QScript login, not IBM cloud login. IBM QScript login. Okay. So once again I will go to IBM and login. So you should land up to this if you are successful in multi-factor authentication. Then just scroll down, you will have quantum labs. IBM quantum lab. If you click on this, you will land up to the computer login. So I think some 70-80% of faculties are able to do it. Hello everyone. Yeah, attention. I assume that 70-80% of people have been able to successfully do it. I think there is some multi-factor authentication issue. I don't know why, but you try it on with some other credential like relatively. So what we focus today on is basic thing is you have to create your MFA, get the API token, successfully register on IBM QST login, and IBM opens up their quantum computing as a service, okay, exposed to IBM cloud at the backend. You don't have to log into IBM cloud specifically. IBM QST with an API token will expose you to two types of quantum hardware. There is something called as quantum simulators. Quantum simulators are those devices which are actually superconductors and supercomputers, classical supercomputers. These classical supercomputers are used in some data center of IBM to simulate a quantum system. Okay, I will come to that. What does that mean? We will come to that. That is called as quantum simulators, which means that up to 2 raised to 30, 2 raised to 20 qubits, you still can have large supercomputers which can work and give you 20 qubit system, 10 qubit system. So likewise, they in the backend actually simulate the quantum hardware model. But in principle, it is a classical supercomputer at the backend exposed to cloud computing service. Now, second are the real quantum computing hardware devices exposed through the cloud computing service of IBM. So these actual devices also you can ask for once you have run an algorithm. Okay, then there is a demand queue generated on the cloud computing to IBM QST. So let's say because I am demanding for you provide me for let's say 1 second time of your quantum computing hardware. Somebody else might be demanding it from somewhere else in the world. So through cloud computing for the respective data center where that physical quantum computer exists, it will queue up our job and accordingly whenever it is available, it is release that resource first. And our algorithm will be physically then transformed and deployed on that physical quantum computing hardware device somewhere sitting in the United States or whichever is the data center. That is how it works. Same concept as other cloud computing hardware, how they are exposed to cloud computing services. Now before going to this point, where we have QST tutorials, these tutorials, quantum challenge, etc. etc. We have multiple things. If you click on QST, you go QST, then you have algorithms, circuits, advanced circuits, operators, simulators, textbook. Okay, so here this is your cookbook. Actually, to understand what are the ingredients you use to actually create your recipe on IBM QST. But before moving to here, you will need to understand the concept of quantum computing from a mathematical perspective. So let's move to quantum computing for computer scientists. This is a PPT, and let's understand this particular. Representing classical bits as a vector. So which is also called as Brand-Ket notation in quantum mechanics. Okay, so this is ket, 0 ket. Okay, and then there is something like this bracket, and you can write something which is called as Brand notation, which is ket notation. So this is overall called as Dirac vector notation in quantum mechanics. So now what we are doing here is that if this is a classical bit, if classical bit 0 has to be represented in this format, which is using linear algebra, I am representing it as a 2 by 1 column matrix. So this is classical bit 0, okay, with the value 0 as 1. So which means that this is the value 0 and this is value 1. So this is the state space actually. This is
this particular specification.
no, this you will have to download it from. You just type quantum. It's not there. Microsoft, you will get it from YouTube, or you also Google, you will get a complete video of this presentation. The name of the YouTube video is Quantum Computing for Computer Scientists, and there is a book also with the same name. Okay, this is part of Microsoft research in 2016. It is freely available. You can download it from Google. So let's understand how a single classical bit is represented mathematically in quantum computing. So you have state 0 having the value as 1 and state 1 having the value as 0. So explicitly we are having two different places here for representing the state 0 and 1 of a classical bit. So this means that there can be only two states in a classical bit, either 1 0 or 0 1. Please let me know if you understand this much. This is simple algebra, but this is classical single bit with a value 0 is this 1 0 column matrix, and single bit with a value 1, also denoted in Dirac notation like this, is represented like this 0 1, which means that 0 state is having value 0, which means 0 is not there, and 1 is one state space is value is having 1, means 1 is present like this. So in classical bit you can either have a 0 or a 1. Okay, this is how you represent it. And you will come to know why we have represented it like this. Okay, in this linear algebra format as a column matrix of 2 by 1. Okay, ideally complex qubit values are actually complex numbers. So for simplicity in this Microsoft PPT, we are actually doing it as real numbers. So if it is a complex number, you will have x plus I. x1 plus I1, x2 plus I2, so which means that instead of a single value you will have 4 values for one qubit. But for our current mathematics understanding, we are assuming that these are real numbers, the values of qubits, but it is mathematically represented as a complex number ideally. Okay, but so this is 0 and this is 1 bit. This is a classical bit 0, classical bit 1. Now let's move downwards. Basic multiplication of two matrices. This we all know. This is if we want to represent it like this. So this is matrix multiplication. I will not go into this. Then operations on one classical bit. There are 4 types of operations that we can perform on a single classical bit. Okay, this is again basic mathematics, identity operation. So if it is a single bit, I am performing identity operation on this single bit, so it is unchanged. So the effect of identity matrix on a single bit, okay, its state space remains unchanged. So this is 0. 0 remains 0 and 1 remains 1. Now other operation is negation, which is this matrix. So this is a 2 by 2 transformation matrix applied on a 2 by 1 state space representation of a single classical bit. So this is 0, 0 goes to 1 after negation operation and 1 goes to 0. Okay. Similarly, constant 0 is an operation where your 1 remains unchanged, 0 remains unchanged and 1 becomes 0. So it converts everything to 0. And there is constant 1 which converts everything to 1. So if it is 0, it goes to 1, and if it is 1, it remains as it is. These are the 4 unitary transformation operators applied on a single classical bit. Just let me know if you are okay with this. Right? Now, in quantum mechanics, all systems are typically reversibly computable, which means that you will have all operators in quantum computing are reversible. So you will never find any operator that is not reversible. Okay, so that is why these four operators, which are single qubit operations, here constant 0 and constant 1 are non-reversible operations, which means that if I give you the output alone, there is no way to identify what was there. So constant 0 is a irreversible operation and constant 1 is also irreversible operation. So they do not apply to quantum mechanics. So this is one difference. Okay, cover it. So this is, so we understand this is the value of 0 is 0. The value of 1 is 1, which means that this is the value 1 for a classical bit. It gets converted into value 0 of a classical bit. This is state space. There are two states for a classical bit. What are those two states? Two values, 0 or 1. These two values are represented by a 2 by 1 column matrix. Okay, either 0 1 or 1 0. So instead of writing if there is a 0 in a classical bit, mathematically we are representing it, and you will come to know why we are doing it. Because if you want to represent qubit, you can have 0. You can have multiple things in related to qubit, where you can have fractional values sometimes, etc. So that we will come to that. But as of now, hold on to it. So here constant 0 and constant 1 are operations on classical bits, but they are not applicable on quantum bits, that is qubits. Because these are irreversible operations. That's the only thing that they are doing. That is what this all talks about. Identity and negation are reversible, so we can use identity and negation as operators on quantum bits, that is qubits. So again, the same thing. Repeated. Now, the tensor product of vectors. So, if I have, so tensor product of vectors is used to represent multi-qubit state space. Okay, if I have 2 qubit states, okay, if there is 2 bits here in a similar fashion, 2 bits or 3 bits. So if I have 3 bits, for example here, if you have 2 bits, okay, then 2 bits means I have 0 0, 0 1, 1 0 and 1 1, 4 states. In the state space I have 4 states if I have 2 bits or 2 qubits. If it is 3 bits or 3 qubits, I have 8 states. So 2 is to n states are there in a n qubit system. Okay, so this means, I will come to this, but this is 0 0 0, 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0 and 1 1 1. So these are the 8 states for a 3 qubit or 3 bit system. So we are representing states that a system can take for doing computations on those states. Now, if I have values for all these 3 qubits, for example, out of this the first bit is having 1, second bit is having 1 and third bit is having 0. This is actually the value 0 is true, means it is having a 0 value, third bit. So it is actually 1 1 0. So you have to check, this is 0 0 1 0 0 0 state, this is 0 0 1 state, this is 0 1 0 state, this is 0 1 1 state, this is 1 0 1 state, this is So this is 101 state, this is 11, sorry, 0. So actually if you calculate this will be 110, this is 110 and then 111. So 110 is true, means it is, and what is it actually? It is a tensor product of individual qubit states. So a multi-qubit state or a state space representation is nothing but a tensor product of individual qubit states. What? Sorry?
Decimal numbers.
They have shown tensor product in terms of it. Definition of tensor. Just in order to showcase you the calculation. But values are always either 0 or 1. So same with examples. Same thing. See, here they are elaborating the same thing. This is 4 basically. 100. So 100. And if you calculate the tensor product, it will exactly come like this. Now there is a 2-qubit operator. This is a 2-qubit operator called as C naught. Yes. Because this is a tensor product. So this is state 1. So how is tensor product calculated? They have shown it here. Okay, this is how you calculate the tensor product. So C naught gate, again now this is a gate which is in mathematics a multi-qubit operator. Okay, so multi-qubit means it is a 2-qubit operator, which means that it will be having 4x4 matrix. It will be a 4x4 matrix because 2-qubit state space is a 4x1 matrix. 2-qubit state space you have 0, 0, 0, 1, 1, 0 and 1, 1. So 4 states. So for a 4x1 matrix, the transformation operation will always be a 4x4 matrix. So this is the transformation operator where it is like in an identity matrix, you just flip the rows or columns. The last 2 columns or last 2 rows, you just flip. That is a C naught operator. That is called a C naught operator. This is the C naught operator. And what does it do? This is what it does. It has 2 bits basically. It operates on pairs of bits, one of which is a control bit and the other is a target bit. This is similar to the way gates were devised in digital electronics. So if the control bit is 1, then the target bit is flipped, and if the control bit is 0, then the target bit is not flipped. It is unchanged. So it acts as an identity operator if the value of the control bit is 0, and it acts as a negation operator if the value of the control bit is 1. And then this is an example of a C naught operator. Okay, with example. So now you have, if you have 1, 0 as a 2-qubit state, if you apply C naught operator on that, then it becomes 1, 1. This is how transformations are applied on multi-qubit states. Now we will go to qubits and superposition. Now because of superposition, in the representation is similar for a classical bit and a quantum bit. The difference lies here. Qubit can have values like this. Qubit can have values of superposition like this. 1 by root 2, 1 by root 2, which means that the 0 value is having half probability and occurrence of 1 as a value has a 50% probability. Because superposition can exist in qubits. So let me know if this is. So in a qubit is represented by column matrix AB, where A and B are complex numbers, and complex number because it is on the values are on a qubit, that is a block sphere. So it is restricted with this condition, modulus is 0, is 1. So because all values should lie on the surface of the sphere, this is the limit for that. If this is strictly less than 1, then it will be inside the sphere, and if it is greater than 1, then the values will go outside the sphere, block sphere, unit sphere in complex domain, right? So if you have A and B as two values, okay, basically representing 0 and 1, then this condition actually so this condition imposes the constraint that all the infinitely many superposition values are on the surface of the block sphere, right? So in an imperfect quantum computing system, you will have recurrence and maybe this condition becomes strictly less than 1, or sometimes it is less than 1, likewise. But in an ideal qubit simulation, this should always be true. Okay, so and how many values can it take? Infinitely many. So there can be such, with this condition holding, you can have infinitely with many pairs of numbers which will hold this condition to true. With those pairs. For example, 1 by root 2, 1 by root 2. So the square of 1 by root 2 is half, plus half is 1. So 50% probability of occurrence of 0, like value 0, is 50% probability of occurrence of value 1. Similarly, here this is 1 by 4, so 25% probability of occurrence of 0 and 75% probability of occurrence of 1. Likewise, you can have multiple number pairs that will satisfy this equation, and that is the difference between the qubit and the classical bit. So classical bits are actually subsets of qubits. All classical bits are qubits, but all qubits are not classical bits in the state space, because 0, 1 and 1, 0 are the two pairs which exist for classical bit, which is also true for qubit. So similarly, if it is a multi-qubit system, if it is a 2-qubit system now, for that the probabilities of occurrence of all the bit states here should add up to 1. So this must hold true. So mod of AC square plus AD square plus BC square plus BD square is equal to 1. This should always hold. Again, we cannot visualize this state space for multi-qubit system. Okay, from a geometrical perspective, right? But it was something like a hypercube or some hypersphere. We don't know. It's in higher dimensions. Okay? But mathematically, this is still the constraint. So that was in 3-dimensional space, a 2-dimensional surface. It is a sphere. This is now moving in 4-dimensional space. So operations on qubits. Okay, so now same thing. We have operators which are also called as gates. Okay, or sometimes all operators might not be gates, but if we represent it from a circuit, we call it as gates. But there is always some operator that is a two matrix transformation operator. So for this qubit, this can be a negation operator, right? Which is just flipping the values. Again, now because now we have this kind of values for qubits, okay, for a multi-qubit system, we can again form tensor product and get a state space for a 2-qubit system. So this is the state space for single qubit, this is another state space, and we are getting a multi-qubit state space, that is 2-qubit state space. These are the values 0, 0, 0, 1, 1, 0, 1, 1. Here it starts getting interesting. Now this is your gateway from classical to quantum and quantum to classical. Okay, so we know that the state space for classical bits is, or a single classical bit is either 0 1 or sorry 1 0 or 0 1. Correct? So that is, it is either 0 or 1. Only two values. But in quantum domain you can have these kind of combinations. Okay, now there is something called as Hadamard operator, which is a 2 by 2 matrix, okay, which is a single qubit operator, okay, which converts your classical state space into quantum domain, and it converts back. It is again a reversible operator. All operators in quantum computing are always reversible. Now, so if it is 1 0, there is 0, it goes to 1 by root 2, 1 by root 2. Okay, this is the Hadamard operator. And if you apply it on 1, it will give you, so this, like this, it will give you back the quantum domain from this value. If you apply the same operator on this, you will get back this state again. And if you apply this operator on this vector, it will again give you back the 0 qubit state. And this is a very important operator because this is your starting point to convert our classical data into quantum domain. From a circuit model perspective, this is quantum circuit model computation. Okay, so that's the same thing which I was talking about. If you reverse transformation, this is reversible. If you apply it on this qubit, it will give you classical state.
So like Hadamard, we can use any other transforms also over there.
Sorry? Yeah, yes ma'am.
Like Hadamard, we can use any other transformation over there.
Yeah, so there are multiple operators and gates, right? Hadamard is one type of single qubit gate. Another one is identity gate that we saw. Another one is negation gate. Constant 0 and constant 1 will not apply. C0 is for 2 qubit systems. So again, so likewise for 3 qubit there is some other gate. There is something called as CC0 for a 3 qubit system. So it has 2 control bits and 1 data bit. So one flipping operation. And now this is an analogy because this is only real numbers we have used. All the transformations can be visualized as states on a unit sphere. So this is a unit circle. Okay, ideally this transformation occur on a block sphere. The values gets changed for a single qubit on a block sphere. Single qubit will always occupy value on a block sphere. Okay, so similar, so now this is 0 1. So block sphere will have 4 by 1 matrix, so because it is in complex domain. x1 plus I by 1 and x2 plus I by 2. So instead of that, we are just visualizing it in a circle, forgetting the complex part as of now. So if we apply a particular operator on this value of a single qubit, what will happen? Which operator applied on this value will happen? So this is series of operations on a single qubit. How they get affected? How will you convert the value of a qubit from one value to another value using multiple operations? Can be visualized using this unit circle visualization or unit circle statement. For example,
From 0 1 to we are going to 1 0.
0 1 to 1 0, which is negation operator.
Negation operation. Okay.
So this is only negation operation demonstration, right? For example, if I am only applying negation operation, so 1 0, let's consider there is 1 0, this is 1 0. So 1 0, first negation is applied, so it goes to 0 1. So it goes here. Then Hadamard is applied, so it goes to here. Then after Hadamard again negation is applied, so it goes to here. Then again Hadamard is applied, it goes to here. And then again negation is applied, so it goes to here. So if you want this state to be converted to this state, you have to apply these 5 single qubit operations in this particular sequence. Okay. That is how you change the value of a qubit from some particular value to another value using a series of operations. So this is very important to understand. If you don't understand these operations now, those circuits and IBM you will not understand. Okay, so I typically stop here with this because I think this is the most important concept in understanding the mathematical framework behind quantum qubits, basically, then quantum circuits, operators, gates on quantum qubits. Now there is something called as an oracle. Oracle in quantum computing is nothing but a black box function, which is nothing but ideally a transformation operator, where you don't care about how it is implemented internally, but it acts more or less like a function level procedure. This is again a framework that has been built in order to accommodate certain particular conditions. For example, you still can process irreversible operations on a quantum computer by adding extra bit of information to denote some of the, like we add a parity bit and all in our classical communication protocol. You can add metadata which will represent certain information about the input data, and then can implement the reversible operation. But it is at the cost of doubling down your input state. So for a single qubit, if you want to implement the irreversible operation, you add one more qubit which will tell you like this. Okay? So it is at the cost of loss of your memory or loss of your information occupation. But it will still work. So you can still use analogies in classical programming in some or other means by tweaking it using quantum computing. So that's what this talks about. See, so this is input and output, and now you before and after. So this is what they are doing. I just explained this. So how do we write a non-reversible function in a reversible way? So you add one more information for that particular bit as an extra bit. So now, earlier we thought a constant 0 cannot be implemented on qubits, but with this Deutsch oracle concept, you can add one more input bit and then you can implement constant 0 operation also. Same with constant 1 operation. And this is the circuit diagram for implementing constant 1 operation as a Deutsch oracle. Deutsch was a scientist, there is a famous algorithm, it is Deutsch algorithm. The first algorithm is so this is his name is given to this oracle concept. So that is how we are, this is a common hack. Add an additional output qubit to which the function action is applied, etc. And this is very easy to understand. You can understand this. And now with these things, now you can implement an oracle which is more or less like a black box by adding one more bit for identity, negation, constant 1, constant 0. And now you can have multiple operations on multiple single qubits. Simultaneously, it is represented here. I will not show any details here. But all four operations you can actually understand simultaneously. So input state you can be like. So this is what this PPT talks about. And then this is all about the same thing, how we will implement it also. And then next is quantum entanglement and teleportation. We will not cover it today. But these are some of the other experiments that we can try based on entanglement and teleportation. This is very interesting. Now this is the right time to go back to our ideal tutorials. Now because we understand what are the different types of representations for a single qubit or single qubit, and then multi-qubits, how they are represented, then how are operators applied on multi-qubit systems, single qubit systems. Now it is a time to define different types of operators, single, 2-qubit, 3-qubit, multi-qubit, etc., so that we can perform transformation functions on our qubits. Okay, and that is what is a quantum circuit about. Now let's go to operators. Then again there are gates like polys, rotation gates, etc. So you can have a rotation, if we talk about the rotation of qubits on the qubits, you can have a rotation transformation applied on a particular qubit, so it will change its phase angle accordingly. Circuit basics. We will go to circuit basics. So here, again this is Python language. So let me know if you are with me. Circuit basics. Again this is all typed. You don't have to type, but if you yourself actually type in by creating a new notebook also, it will work. So basically what we are doing, import numpy as empty, which is we are importing the numpy library for numeric calculation. Then from QSKIP, import quantum circuit. So this is the library called as QSKIP, from which we are importing the quantum circuit. Right. So if I click selected this, and I will just click on this run the selected product. So I am running it now. Is run. Now I have started building the circuit. So the method is CIRC is equal to quantum circuit, and I have given parameter as 3, which means that I want to build a circuit with 3 qubits. Now we want to apply different gates on that particular qubit. Which qubit? So for example, we want to apply Hadamard gate on the first qubit, then C0 gate on the first and second qubit, and then C0 gate on the first and the third qubit. Okay, so what will be the effect of these operations is we want to see. Now this has executed, but for to see the result, we will have to visualize it. So we are using circ.draw with the parameters, and this is where it is visualizing the circuit that we just created. So this is the circuit. On the first qubit, it is a single qubit operator, Hadamard, that we applied. Then C0 is represented like this, because it is a 2-qubit operator. For the first and second qubit we are applying C0. So there will be one control bit and one bit with the value. So this is a control bit and this is again a control bit for this first and third qubit. So this operator is applied to these 2 qubit states basically. So whatever will be the value of this qubit and then whatever will be the value of this qubit, the tensor product of those, this C0 will apply on that tensor product because it is a multi-qubit state at this time instance. So in a quantum circuit analogy, the y-axis represents the qubits, the number of qubits. This is a 3-qubit system. The x-axis represents time. So this operation is happening earlier, then this operation is happening, then this operation is happening. Okay, so we will apply this. Then whatever state this qubit is, it will flip. So if it is 0, 1, 1, 0, it will accordingly flip into 1 by root 2, 1 by root 2. Then this 1 by root 2, 1 by root 2 with whatever state this has, this will get transformed. Then whatever will be the state, this and this, you have to calculate the multi-qubit tensor product and then the state space will be there. And then this C0 operator will be applied on that. C0 operator is the same 1 0 0 0 0 1 0 0 0 0 0 1 and 0 0 1 0. Okay. So this is how we have to understand what is happening in terms of, so this is the C0. And now if we want to see what is happening after this, then this is what is happening. So then we are passing on some values and then we are verifying whether our circuit is giving us the correct results as expected. So if you calculate it, you will get the same results. And then we can also draw that state dot draw. We can also draw log sphere representation.